This technology stack operationalizes the TFP Stability Paradox, a stochastic modeling and simulation system for the algorithmic stress testing of sovereign risk and institutional reliability. Authored and built using validated methods from the fields of economics, game theory, and statistics. It integrates structural modeling, empirical forecasting, agent-based simulation, and AI agent inference to evaluate how productivity-driven economic transitions interact with institutional stability. Moving on to the advanced application for modeling TFP stability, we start with the Synthetic Data and Methods tab. This tab explains how the TFP Stability Paradox application produces robust insights without relying on sensitive data. The system generates synthetic macroeconomic datasets calibrated to historically observed ranges across advanced and emerging economies. Core variables, automation intensity, labor share, inequality, coalition size, and political stability are linked through fixed structural equations defined in the model. Rather than predicting individual countries, the application runs scenario-based simulations to examine directional effects, nonlinear dynamics, and threshold behavior. The Indexing and GIS tab visualizes the core dynamics of the TFP Stability Paradox through a spatial risk and dynamics index. Rather than mapping productivity or growth directly, the model translates underlying economic relationships into geographic patterns of stability risk. Each index value is derived from the model's structural equations linking automation intensity, labor share compression, income inequality, coalition size, and political stability. These relationships are fixed in the code and applied consistently across synthetic observations, allowing us to observe how small changes in productivity dynamics propagate into social and political outcomes. The GIS layer enables analysts to see where these pressures concentrate spatially. Regions with rising automation and declining labor share tend to exhibit higher inequality, which in turn shrinks governing coalitions and increases instability risk. What appears gradual in aggregate data often reveals sharp thresholds when viewed geographically. By animating the map over time and across scenarios, the application highlights nonlinear transitions, zones where systems move from stable to fragile without obvious early warning signals. These are not forecasts of specific countries, but structural patterns that recur when the same economic conditions are present. The mapping interface also supports comparative risk analysis. Users can identify clusters of elevated TFP risk, regions insulated by broader coalitions, and areas where intervention windows remain open before instability accelerates. This spatial framing is critical because instability rarely emerges uniformly. It concentrates, spills over, and cascades. The purpose of this tab is diagnostic rather than predictive. GIS transforms the TFP model from an abstract system of equations into an interpretable risk surface, helping decision-makers see where productivity gains may unintentionally undermine stability, and where timely policy responses can still alter the trajectory. The Forecasting tab complements the structural TFP model with empirical forecasts. The application allows users to compare statistical approaches such as trend and ARIMA with machine learning models, including neural networks. Forecasts can be run across variables, time horizons, and scenarios, with uncertainty bands displayed alongside point estimates and fed into simulation analysis. In this example, the model forecasts labor share of income in the United States. Under baseline conditions, results show a continued downward trend with increasing uncertainty. This is not a prediction, but an empirical projection used to stress test assumptions. The Stability Modeling tab presents the core mechanics and results of the TFP Stability Paradox model, linking productivity, inequality, coalition dynamics, and political stability within a single framework. The model captures how automation-driven productivity gains compress labor's share of income, raise inequality, and reduce coalition size, ultimately lowering political stability. These relationships are defined by fixed structural equations and applied consistently across simulations. The objective is not point forecasting, but identifying systemic risk and nonlinear transitions. Shown here is the baseline scenario, run using 500 Monte Carlo simulations. The baseline assumes gradual automation without shocks or policy intervention. Each run introduces stochastic variation around the same structural relationships, allowing us to observe the full distribution of outcomes. The results show a consistent pattern. Early on, median outcomes appear stable, but dispersion increases over time. As labor share declines and inequality rises, a growing share of simulations crosses coalition and stability thresholds well before the average path signals concern. This widening tail risk is central to the TFP Stability Paradox. The tab also allows users to explore alternative paths through scenario controls and preset cases, enabling direct comparison of outcomes, volatility, and downside risk relative to the baseline. The agent-based modeling tab simulates the TFP Stability Paradox, where macro outcomes emerge from individual behavior. Workers and firms are modeled as agents. Firms differ in size and automation intensity, while workers vary by wages, employment risk, and exposure to automation. Firms decide when to adopt automation, and workers respond through wage changes, transitions, or displacement. Shown here is the baseline scenario, run using 1,500 Monte Carlo simulations, each sampling 1,000 workers across 100 firms. The results show how gradual automation produces uneven outcomes, where small differences compound over time, shaping labor share, inequality, and systemic risk even without external shocks. Last but not least, the TFP Stability Paradox application coincides with an AI agent that extends the full analytic stack. All application tabs, including structural models, empirical forecasting, Monte Carlo simulation, and agent-based analysis, are consolidated into a vectorized knowledge layer spanning the underlying code, data, and model outputs. This enables reliable natural language interaction with the system. The agent can recall prior scenarios, reference forecasts, reapply simulation logic, and infer new insights using the same validated assumptions defined in the application. Rather than replacing the models, the agent orchestrates them, transforming the platform from a static analytics interface into a persistent, interactive system for advanced reasoning and decision support. This concludes the demonstration.